Hi, I'm going to do a little bit of a video on the, let's just call it the plane net of the E or T module from Buckminster Fuller's Synergetics, along with the scalene triangle that is the only one that is not a right triangle in the T and E module. And the reason I'm going into this is it's the scalene triangle is part of the golden three-dimensional golden spiral. So we have two red lengths here, and then we have this yellow length, making the larger triangle. And I just wanted to, now I'm just going to show the area real quick. Okay, that area there. What I found through some pretty basic computations of area is that that area of that larger triangle is the same, get rid of it, as the area here of this square. Oops, I missed it. Bink. And then let's say, for simplicity's sake, that the square's edge is equal to 1, and the length and the width are going to give us an area which is 1 times 1. Okay, so that's 1 square unit. And I'm saying that this square that I just showed is the same as the area of this triangle here. And one can compute that by the next larger sized square would be an edge of 1.618 by 1.618. Well, the interesting thing about the golden mean is then that would make the area 2.618, or the area of this larger square is 2.618 and the smaller square is 1. So the difference is 2.618 minus 1, or 1.618. And that is kind of like the linear progression of the golden proportion, but now it's areal, so it's to the second power, the increase. If you increase the edge by phi, going from 1 to 1.618, you square phi, you get 2.618. That's pretty rudimentary stuff. So if we were to calculate the area of, I'll take those out now. If we were to say, well, how do we prove that? Well, we could, I shouldn't have taken them all out, but anyway, that larger square has 3 triangles besides that larger interior triangle. So here is one of them. And we can say, well, that edge on top here is 1, and the edge here is this overall length. I've got in pieces, but this overall length here is 1.618. So we go 1 times 1.618, and we're going to divide it by 2 because that's the area for a triangle, and we get 0.809. Let's just round it off there. So then we have this other triangle that's similar, same angles, and actually the longer edge is 1, the shorter edge is 1.6. It's just 0.618. So 0.618 times 1 is 0.61 divided by 2 is 0.309. And lastly, we have this triangle here, which is 0.618 times 1.618. This edge being 0.618, and this one being, and that is equivalent to 1 divided by 2 is 1/2. So if we add together 0.809 plus 0.309 plus 0.5, we get an area of 1.618. Which means if the overall area of this square was 2.618, we've subtracted 0.618, and we have left over 1, and the area of this inner triangle is 1, which is the area of this square right here. Therefore, their areas are the same computationally. So playing around with it, that's why all this other stuff is in here. We take this triangle right here, and I can't actually see the, for whatever reason, I'm going to have to get rid of that. I just want to be able to highlight that little dot there. If I take this area here, that's part of this square. That's exactly right here. That's the same as this area of this triangle. You'd actually just, if it was cut out, you could slide it over there. And that's essentially, we're filling in this, we know that this area here of this smaller scalene triangle is shared. That's a shared area. So we're not concerned about having to slide that. It's already in place. So that's taken care of. And now this larger, these two triangles are the same. And now we have, oh, I took that line out. We'll put that back in. There's another area that doesn't have to move. Oh, I don't do that either. But anyway, we have this triangle here, which is part of both the larger scalene triangle and of the square right here. And then we have this area here, this smaller one with the yellow edge. Well, that's the same as this one right here. And then the only funny thing left is we got this chunk here that we haven't taken care of, which includes a smaller yet scalene triangle. But as you can see, this triangle here, can't click on that dot very easily. Sure makes life tough. Okay, I could do things differently. But anyway, this triangle here, boy, my accuracy's bad. Boink, boink. That one there, which, no, it's really killing me, is the same as this one up here. And same with the, well, I don't even know what I did there. I want to go there, it's just messy. You have this triangle here. It's kind of a foregone conclusion, and I'm having, you know, obviously technical difficulties with the nuances of this. These small hubs, which somebody seems to think are too big on the regular scale, which makes it hard for me to navigate, but they want to, you know who you are, Kirby. Anyway, that area is left over and that area is left over. And it's funny because that area, we filled everything else in. I want to actually get that done because, oh boy, it's just too frustrating. Small little dots. It's terrible. So many things going wrong here just because I have these small little teeny hubs. Okay, so what I'm saying is that this little triangle here, I just want to make it all filled in. And this one here, see, look at that. Try your hardest, you know, it's really quite a small area to try to hit. I missed. See? Twice as much time's taken up because they're such small hubs. Okay, I'm blaming somebody else. Anyway, not fair. But now, as you can see, I filled in both areas. But what we hadn't done was this square and this triangle, and you can kind of tell that this square in relation to this triangle is the same as this overall square here to the overall triangle here. So we're actually repeating the initial cutting and moving of the triangles to show the area. We're just repeating the process ad infinitum. And that's all I'm going to do. It's a damn near 10-minute video. All right, bye.